I'm very happy to be here. So my talk is going to be self-moving oil droplets, which I have been working for about 2 years, and try to make a link between my experiment with original life problem. Let me briefly introduce my background. My background is artificial life. So artificial life, some of you may know heard about this one. So it's basically try to understand life by making artificial systems, which is started like 1987. So artificial life is classified into 3 different categories. One is self-reproduction. How to understand self-reproduction? Right, it's one of the main topic in artificial life. And second one is how to make evolutionary systems, which is also have been done in computer simulations. And third one is a robot. So how to make a self-moving robot entity is the third criterion. And people have been studying all these stuff for the last 20 years, but it's also starting from 15. So this is starting from the cybernetics. So it's my personal notes of what people are doing. Do you have a one person? No, you don't. Oh, this one. Yeah, thanks. So as you see here, so those 3 categories is corresponding to these branches. It's going top to bottom, right? So this one is how the people have been studying self-reproduction, right? Starting from von Neumann. Because von Neumann is one of the first person says that self-reproduction is one of the important characteristics of living systems, right? And the second one is Alan Turing. Alan Turing is, of course, also interested in self-reproduction, but he's also interested in how to make evolutionary systems. And these are the followers of Alan Turing, down to say that Kunikanen gave talked about how to understand evolutionary systems, but it's also he's been using Alan Turing's formula to understand how the evolution proceeds from the chemical reaction networks. And the third one is robotics studies, starting from Greywater in 1949. He made an interesting cargo robot, which is play around, just play around, doesn't do nothing but just moving around. This kind of stuff is one of the first robotic studies, and since then people have been studying it. Bradley Belt and Jordan Clark, Bruce Brooks, and Piper. Then there's doing this bunch of interesting robotics works that came out, right? So it's something is coincident with it was 50s to 60s and 70s. We have the Game of Life, and also the Stuart Altman proposed the automata network, right? Sorry about that. Then 1980, there was the Chris Rankin studied artificial life, and also Stuart Altman, and then the Paul Walls, and also that Francisco Varela and Mastrana gave an interesting philosophical investigation on living systems. Then boom, there's artificial life. So Tom Ray and other interesting people came out and tried to understand the living systems by making artificial systems, not just making a cellular system, but it's making a robot or making a computer program or making some other chemical reactions to mimic living systems. Then just give you one example of how we can make a robot. So this is the sound light seeking robot I'm now working with my students. This one is try to seek light and also the sound and try to code it, right? But without internal neurons, with just plastic connections between sensors. So kind of my idea is that dynamics is not within the robot, but because of the interaction with the environment, the robot can move around, right? That's the idea. And then, for example, like this guy is a robot, taking a video from the ceiling, and there's the ball. So the first of all, robot is doing sort of trial and error, and then finally he sort of find out where the sound source is, and then he's approaching to the source. So this is what people, so this is not typical, but it's one of the examples of how the people are using robots to understand how autonomous motion emerges and to go towards the source. Right? So one of the messages here is that embodiment makes some difficult problems simpler. So people think if the computer program doesn't move around, doesn't have a body, that problem usually becomes so complicated. So it's hopeless. But once you just, without thinking in some complex way, just put in a robot, then that problem becomes easier. So that's kind of the spirit that people are working with. So as I said, the artificial life is a three categories: self-reproduction, evolution, and robots. But the problem is, in order to discuss these problems, we need individuality or the unit, right? So that's what I'm going to talk about today. So this is what self-reproduces is we need a unit that self-reproduces, right? And then what evolves is we need a kind of unit that evolves, right? And then we need a unit that moving around. So these are the robots. So in order to understand these three branches, we really wanted to understand what is autopoiesis is. Autopoiesis is something that maintains its own individuality and shows these three interesting properties. Right? Probably you guys know a bit about autopoiesis. The autopoiesis is like the simple definition of autopoiesis is that self-organization is circular link between a metabolic network and a membrane. I mean that there's a metabolic cycle is going on here. That the production of this metabolic cycle makes membrane, right? And because of this membrane, the metabolic cycle works. So these are the chicken and egg problem. So how these metabolic cycles and a membrane is internally linked together is how the autopoiesis is coming out. These are very much theoretical and philosophical arguments, but one of the guys called Peter Luigi in Switzerland, and also Francisco Herrera, he's a philosopher, but he's a chemist. They elaborated simple chemical reactions to study autopoiesis, and whether this autopoietic idea can be possible with simple chemical reactions or not. Then, using simple surfactants with SXL or sodium like this one, then makes reverse micelles do exactly what Francisco Varela wanted to have. Right? So this reverse micelles has a reaction inside, and then also they try to maintain its membrane. And then also the interesting side effect is once you have this kind of systems, self-reproduction can be obtained as a side effect. So you don't have to elaborate to make a self-reproductive properties, but self-reproduction can come out as a side effect of autopoietic systems. Also, with other people like Peter Wall, and then also the Luigi's group, made a fatty acid vesicles, which makes a tiny little vesicles can also do the same thing. So the previous one was micelles, but this one is a vesicle. So vesicles in the size of like 200 nanometers can also have the autopoietic properties, right? And then quite recent, Professor Sugawara in University of Tokyo group, they also made a gigantic vesicle which can be autopoietic systems and also producing in a time scale of like this. After 1 minute long, or after 5 minutes, they make another vesicles. So these are well, I think it's an example of how you can make the real autopoietic system using chemical components. Then I come to my theme. So how do I make making self-moving autopoiesis? So as I said, evolution, self-reproduction, and then robotics is the three main branches in artificial life. But in order to understand these branches, we have to have an autopoietic unit somewhere, right? And then once you have an autopoietic unit, do you think we can make a self-moving unit or something? Like we made a self-regression properties naturally from our autopoietic unit. So, so I was interested in this one. And studying a moving droplet is interesting because it's designed the way the system interacts with the world. Right? And also sensing the environment and making an action is inseparable from each other. This is sort of a Gibsonian idea of psychology that making action is also making sensing towards the environment. Also, making action is to organize the relationship between the system and the environment. So it's not just an independent something that is making an action, but it's more like a relationship between environment and system. And self-adjustment is what we call self-organization of the making action. In this sense, the primitive cognitive system appears when self-movement emerges. So these are the reason why I'm interested in self-movement. Because once you have a self-movement, you can have a primitive and a minimal cognitive systems in a pretty much a cellular level or the chemical level. Right. And this is the sort of the automaton evolution, well, the automaton simulation of how the autopoietic entity can move around. I did with this one with Keisuke Suzuki and myself 4 or 5 years ago. So this is the simple chemical reactions. Like L is for the link particle. When L, first of all, when substrate, two of the substrates coming to the neighborhood of the catalyst, then they are making a link particle. And when there's a link particle neighboring each other, then they are linked together and they make a boundary. Therefore, the catalyst is enclosed within the boundary, and then the reaction goes on and then try to maintain the boundary. At the same time, this guy is moving around. So this simple cell automaton tells you that once you have a simple artificial chemistry, then you can have a autopoietic system. But at the same time, maybe they can move around. But we're not quite sure whether this is possible in chemical systems, the real chemical system. Then we try to make the real one. But my background is theoretical physics, and then I can't do experiment, But because of there's a genius chemist, two of them. One is Taro Toyota from Tokyo University, but now he is in University of Chiba. And then also Martin Hungry. He's now in University of Southern Denmark, but he's from Harvard. These two chemists have helped me to sort of elaborate this idea of self-moving droplet and how we can make it and how we can play with it. Now, this one is so simple, so finally I can do it by myself. So I tell you what the chemical system is. The system is so simple. First of all, you have to use the oleic acid system. The pure oleic anhydride is the oil part. And then water part is like a high pH water. High pH is made by, say, soda. And the pH should be in between 11 and 12. That's the condition that I know, right? So the oleic anhydride is the main part of the olive oil. So just go to buy olive oil and then put the soda in the water and then olive oil. Then you can have it. But the problem is you have to have a pure system. Otherwise you cannot publish paper. Right? So it's a bunch of contamination in the olive oil that you can buy it. But anyway, so this is the simple system that I'm working with Martin and Taro. And then I have to explain what the chemical reaction is about. This is the oleic anhydride. This oleic acid molecule is connected with this chain. So when there's water, this hydrolysis reaction is called cutting these bonds, and you can make two of oleic acid. Right? And oleic acid is in balance with the water, so the two proton is protonized or deprotonized. That is the equilibrium state. So in some graphic ways, this is water, this is molecular hydrate. Interacting with each other and making a product. This product is oleic acid and then oleic. So this green product, the oleic acid, is a surfactant, so they are covered in the water, the oil droplet, right? And the rest of it is just throw it away from there. That's the main. And what we do is put the slide and then simple dip here. So you just put water, pure oleic anhydride, and see how it performs. Well, usually it goes to the very sort of non-interesting state. Right? Maybe you play with the game of life and you're starting from the random state and just have that. Right? But if you're lucky enough, sometimes you have some interesting behaviors. So let me go. So this is one of the first experiments that I did, and I was lucky enough to record everything. Right? Means that I cannot replicate the same behavior. So people say this is the beginning of luck. So this is the scale of this one is a few centimeters. This part is a pure oleic anhydride, and in interaction with the water, so I didn't put the glass slide cover glass on top of it, so there's a flow structure because of this the surface tension. And after a while, you can see something comes out. So I was interested in these guys. These guys are at a scale of few hundred micrometers. Say after a while they start to move around, which I call oil droplet, autonomous oil droplet entity. As you see, usually they throwing away something from the tail and they go this way. How much are there?
20 minutes.
20 minutes. So this is what I call oil droplet. So this is another take. And you can see some other droplets forming here and also here. This one may not move around, but this guy is moving. So this is not, but this guy. So this interesting population of droplet is emerging from here. So sort of ecology of droplets. This is some of them are never been moving. Like this guy never moves. This guy. And as you see, some of them have some interesting trails, but some of them having that doesn't have that trail. So there's different ways of moving around. So this is another picture. This time I put some scales, of course. So it is 200 micrometers. And you see it's gradually it's moving, and you see the flow structure around it. And also you can see some internal structures, like these chemicals as moving to the leading part. And this is the leading part, and this is the tail part. So this flow, the inside flow is like this way. So these are all the information that we have. So I have to guess what's the mechanism that this part can move around, and then what is the future possibility using this kind of stuff. Okay. So first of all, let's say that the wild experiment is important in the sense that the environment of the droplet means the micelle concentration of pH is white and white, and this one has more like a discrete something leaving afterwards. And also this guy is frequently changing its direction, but this guy has some structures sticking out from the surface and some other structures. So these are the interesting index that, because even if the condition is almost the same, the behavior, the motion structure is different. So now I'm moving on to how can I understand the behavior. But this one is the close fit the movement, how the droplet is moving around. This is a control droplet. So I put nitrobenzene inside the oil droplet. So therefore the reaction is rather suppressed. Therefore it's easier to maintain the structure, and then make a close view of what happens here. And you see the surface is like some membrane or fluid, so sort of unclosing the way that like the behavior is observed. And as you see, these are the convection, as I said, there's a convection flow. When the droplet goes this way, the convection flow goes in the other direction. I forgot to show you. So this is another, but you can see, this is 12, this is 200 micrometers, and you can see the convection flow is occurring, right? And then this one goes this direction. Interestingly, there's another guy, is here. You can't see the convection flow inside, but there's the flow structure around the droplet. And there's the flow from this part to the other part. So therefore, there's an interaction through the medium. So is a chemical flow structure is controlling the interaction between the droplets. That's going to be the experiment and study. Okay. Then I try to make a phase diagram of why when we have these droplet structures. So we change the concentration of oleic in the solution and also controlling the pH. This green area, as you can see, chemical reaction is going on, right? So it's very reactive. So you can see the reaction is going on, right? Making some bubbles and stuff like that. But the reaction itself cannot make droplet move around. You have to have pH conditions or some other thing. In this case, you have to have enough oleic surrounding the oil droplet. Also, you have to have a high pH. Then you can have a movement. You can have the convection. So when the first column said yes, means there's convection. Or when you have convection, and also you have a chemical reaction, then the droplet can move around. But the movement is different depending on how much oleic is within the solution. So that shows that yes, star means that there's a different movement. So these guys, no oleic in the solution, but pH 12 and pH 11 with the oleic because they mean more has the same behavior. So now we put a pH indicator within a droplet and see how the pH changes. But when you see these droplets moving around, and you can see some white trail when the droplet is moving around. Means that the trail has a lower pH compared with the environment. And then white means that pH is lower than 7. Therefore, first of all, the environment looks like a pH 11 to 12, but the trail has a pH 7. And also, this guy is reversing from the lower pH. Therefore, they're trapped by their own trail. That's what the memory effect within the environment. So the droplet, when they move around, they are sort of spreading surfactant after they're moving in the rear side. Therefore, this is accumulated within the environment. Then, because of this lower pH regions, the droplet cannot move freely. And this effect is an interesting effect to the droplet's motion, because once the droplet is close to the lower pH, the convection flow is reversed. Then they try to go away from the pH, lower pH. But when there's a high pH, then this guy goes towards the pH. So therefore, there's a primitive chemical taxis exists within the droplet. So I try to analyze it because my laboratory is a theoretical studies. So this is, but it's not a model, but it's a numerical simulation of the oil droplet. And well, those who are familiar with these equations, this one is an Navier-Stokes equations. It's just simply describes how the flow structure is described. This is a two-dimensional incompressible water. These are the U, vector U is the flow vector at the point x at time t. And the point is, there's the force F is on the right-hand side. Force F is a function of the chemical at the boundary. So when there's more chemical, the force is proportional to the amount of the chemical there. Right? So this is an assumption. This is also taking into account the pH, lowering the pH, and then going up the surfactant. So when there's a hydrogenization, when there's a chemical reaction goes on, the tension goes up. That's experimentally confirmed. And also, this is the variable V is the amount of the chemical. The amount of the chemical is affected by the flow structure. But at the same time, the reaction is going on. So the chemical is generated at the boundary and then diffusing through the space by this term. So basically, coupling this flow structure is the Navier-Stokes equation, two-dimensional incompressible water. And this one is the chemical reaction is affected by the flow structure. Also, we have a density matrix. Density function is also affected with the same schema. So this one is try to determine where is the boundary is. Right? So it's a bit complicated, but it's complicated as it is, right? Because the computer becomes very fast, and like 10 years ago we cannot do this, with this one, but now we can do it in a real time. That's the advantage of this using this direct numerical method. So first of all, we set up the initial condition, and then density function is placed so that the boundary of the droplet constitutes a circle. Then calculate the interface forces using equation sheet. So this F is proportional to the chemical mass. Then solve the Navier-Stokes equations and then continuity equations to get flow structure and then pressure calculated. Then we compute density function and then chemical gravity. Right? Then I check this time. So we try to use the realistic parameters as well. But this is the two-dimensional. The real one is three-dimensional. So this is still approximation. What we found with the numerical situation is that when you have two vortices, it goes this way. Right? So this one is, first of all, starting from the random chemical distribution. First of all, you droplet has 4 vortices, and 2 of them is selected, and then start to move around. So this is the first ball, it was initially there the turbulent state, then 4 vortices appears, then 2 vortices is selected, then it's moved around. So that's what I found. And also interestingly, this is how much distance the droplet moved from the initial state. And there are 2 peaks. One is never moving droplet, and this is moving droplet. So even if it looks like the same, depending on the initial distribution of chemical mass, the droplet can move or move not, does not move. So this is controlled by the initial state. Also, the interesting thing is, because this is numerical computer, you can have a with or without convection flow. So without convection, droplet moves slowly and then decays fast. But when there's a convection flow, it moves fast and sustains a lot. Means that when there's a convection flow, it's coupling with the chemical reactions. This non-equilibrium state, this reaction is maintained. So therefore, the droplet survives much longer than without convection flow. So I skip this. Then I change the droplet size. This is something is a new experiment, but I put 3, 5, 10, 20 microliters, and then 30 and 50. And you can see that the behavior is changing from around this area and around this area. First of all, it's more like spherical to boomerang-like patterns. It becomes more stable, the motion is. But then it becomes like a self-vibrating. So then again, it becomes unstable. Right? So I calculated as a function of size, how much distance they can move from the initial point. And what's the survival rate? What's the lifespan is. So lifespan is getting longer when we increase the size of the droplet. Also, we computed autocorrelation functions. The autocorrelation function always shows linear behavior. And when this is completely linear, it means that this is Brownian motion. But it's in between Brownian motion and then straight motion. So therefore, sometimes it's moving straight, but it's randomly moving and then goes to another direction. And this is the stop-go interval index. So this is how frequently. So this, what I mean by stop-go interval is droplet is not moving constantly. They just go move, stop, move, stop. So I'm just measuring the interval of this stop and go motion, and took the histogram of how this histogram looks like, and then calculated the exponent. The exponent shows that in between this size, exponent goes to 1, means that around this one, the droplet is more likely to move longer than the other regions. This is a way that you can see the boomerang motion. Right. So some of my so this is what happens when you have a huge droplet. The huge droplet has a completely different type of behavior comparing with the smaller ones. First of all, they are moving slowly, like the smaller ones. But after a certain period of time, they takes time. let me accelerate a bit. So behavior sometimes they moving in, like making some strange torus-like behaviors and then vibrate. And we don't know why, but one reason is because when the droplet size is getting bigger, then surface tension is almost constant. And because of the Laplace pressure, the surface is easily modifiable. But also because the Reynolds number is proportional to the space scale. Therefore, there's no beautiful convection flow inside the structure, and it's easily changing the boundary shape. That's what we are thinking. And this one is another example. So this one, they just break up. Like this way. So surface tension balance is of this size is sometimes allowed to decompose into small pieces, which is very unusual in the case of droplet experiment. And interestingly, what I shown here is that doing this numerical computation, above certain size, this droplet is break up. And then when it's break up, the procedure itself is not correct. The procedure itself fails. That is corresponding to whether this strange phenomenon is observed. So I can do it. How much time do I have now?
About.
Now? Okay. Sorry. Let me, favorite book is written by Darwin. It's about earth worm. The earth worm thing is pretty much attractive to me because he says that earth worm is very communicative and interesting guy, and then but the complexity is coming from the interaction with the soil rather than the neural structures inside the earth worm. So when you want to understand how this living system is interesting behavior, that cognitively interesting, you have to understand what's the interaction between the environment and earthworm itself. That's what I'm thinking. And also droplet is interesting because when you have a three droplet, it's not just reversing, but it's coming close together. So this is more like I don't know, maybe it's some spring is a function of the time or something. And also you can have the droplet which is self-guiding by itself. So the droplet is not just moving around, but sometimes you can see the droplet is creating, right? So when you have a